So I'm going to be talking about different finite geometry today, and the three assumptions that we have that we're assuming are true to prove. These are, the first one's exactly, the thing has the shape has exactly 4 lines. The second one's any two distinct lines have exactly 1 point on both of them. And A3 is each line is on exactly, or each point is on exactly 2 lines. So the first thing we're going to do is that I did was I drew the lines, or I experimented with a lot of different triangles, but this is what has seemed to work the best. So the first thing I did was name it different lines. So this is line 1, line 2, line 3, and line 4. So that takes care of the first one. And then the second one is two distinct lines have exactly 1 point on both of them. So this would make sense because if you're looking at line 2 and meeting line 4, there's 1 point that they meet. Or if you're looking at line 2 and line 1, there's exactly 1 point where they meet. Or if you do it the other way, line 1 and line 3, there's 1 point. Or if you look at line 1 and line 2, there's 8, and so on with those ones. Those ones work too. Just don't want to bore you. So that takes care of the second one. And then each point is exactly 2 lines. This makes sense because you look at all these have 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So all the lines are they're 2 lines meeting and coming together and equaling a point. And so we're trying to prove, or what we are trying to prove is it has exactly 6 points. And we can prove this by looking back at our assumptions, so we know exactly that there's 4 lines. 1, 2, 3, 4. And this will give us the amount of dots that we need by looking at any 2 distinct lines have exactly 1 point on both of them. So we got our 6 points by finding every single time the lines intersect. Every time the 2 distinct lines intersect or have 1 point on both of them, which basically means intersect. So intersect 1 time. So line 1 intersects here, it intersects with line 3 here. Line 2 and line 1 intersect here. Line 2 and line 4 intersect here. Line 1 and line 4 intersect here. Line 4 and 3 intersect here, and line 2 and 3 intersect here. So that proves there's 6 points, and especially because each point is exactly on 2 lines, is like I showed before, these are all exactly on 2 lines, so that makes sense. The second thing we have to prove is each line has exactly 3 points. So we have to look back on our assumption. So exactly 4 lines that works. So we have 4 lines, and any 2 distinct lines have exactly 1 point on both of them. So this makes sense because every single time the lines intersect, there's a point. So 3 points because the line gets intersected 1, 2, 3 with 3 different lines. It gets intersected by 3 here, gets intersected by 1 here, and gets intersected by 4 here, and so on and so forth for the other ones. They all create up 3 lines because they're all interweaving. I don't know. They're all connected in some way. So that basically shows how we prove that the shape works for, or this thing works for the assumptions and what we're trying to prove.